Hi there, it's Christopher, and recently I've been working on practicing some mathematics. Now, since I work better with space and rockets than I do mathematics, I thought that the best way to do this would be to apply some of those mathematics to a space-related problem. And what I came up with was trying to work out the mathematics of a satellite constellation. Now, this would be, in theory, a low Earth communications satellite constellation like that of SpaceX's Starlink. What I aimed to do here was to build a theoretical constellation out of 9 CubeSats. So I had 3 main questions going into this. The first question was, what altitude should I place the orbit such that the 9 satellites would be able to see each other? The second question was, what are the dimensions of the transfer orbit such that every time that orbit intersects my final orbit, I can release a satellite? And finally, what is the delta V that each satellite needs from transfer orbit to final orbit? Now, I decided to write everything down, and further along the video we'll be simulating it using KSP with Realism Overhaul. But here's the first page. So if you can't quite see it, what it says is that I have this part right here, that's planet Earth. This inner circle is planet Earth, this outer circle is the orbit line, and these line in this kind of square formation would be the geometry created by the line of sight from each satellite to each satellite. And what I wanted to do with this was to see how large I had to make that outer circle such that the square wouldn't intersect the inner circle. So the mathematics here are that n, the number of satellites, is going to be 9. Our radius of Earth is a known constant of 6,370 kilometers. Radius of the orbit is what we're trying to find. And theta is going to be the angle between satellites. This will be important a little bit later. So the math is such as this. The angle is pretty simple to figure out. It's just 9 minus 2 times 180 degrees over 9. That equates out to 140 degrees. So each satellite will have a 140 degree angle from one satellite to the other. And the radius of the orbit was defined as 6,370 kilometers divided by the sine of that 140 degrees over 2. Now, this is mainly working with circumscribed and inscribed polygons, so that's where I got the math for that. And turning out that equation, I got a semi-major axis, or radius from the center of the Earth, of that orbit for 6,779 kilometers. Now, so I can simply subtract that 6,779 kilometers from the 6,370 kilometers of the radius of the Earth to get an orbital altitude from sea level of 409 kilometers. Now, one of the other things that I wanted to figure out was the orbital period, and I just used a calculator for that since the math got a little bit difficult at that point. But that turned out an almost exact 5,555 seconds for one satellite to complete one full orbit. So this answered the first question. What are the dimensions of the final orbit for the satellite constellation? From there, we had to work out, how do I get to said orbit? Now, the way that they do this in the real world is that they have an orbit that is slightly faster or slightly slower, such that every time it intersects the intersects the final orbits, they can drop off a satellite, and that way they can evenly space the satellite. So right off the bat, I knew that I couldn't go inside the orbit and make the transfer orbit a little bit faster, because that would intersect the Earth. I worked out the mathematics on that, and it would intersect the Earth. So what I tried doing was making the orbit slower. So what we can see here is that this is the point where the two orbits intersect. The innermost circle is Earth, and then on this side, this circle is the final orbit, and that circle is the transfer orbit. Now, through some fancy mathematics, these semi-major axes of that transfer orbit are the perigee and apogee of that orbit are equal to twice the semi-major axis. So we first just have to find out the semi-major axis of this orbit. Now we know that the final orbit through Kepler's law is going to be 5,552 kilometers. So therefore, applying the same one, and T initial is going to be 1.1191 times F, equating in 6,169 kilometers. So therefore, finding the semi-major axis of the transfer orbit, we can apply one of Kepler's laws again, this one right here, and we can get 7,744 kilometers, or 7,744 kilometers. From there, it was simple to work out that apogee equals 2 times the semi-major axis minus perigee, and solving for apogee, we get a perigee, or solving for, apogee, we get an apogee of 6,782, we get an apogee of 8,709 kilometers. Now we can kind of check our math already here, because that is a little bit higher than the final orbital radius of 6,779 kilometers. And if we again subtract that number by the radius of the Earth, 6,700 kilometers, we get an highest point in the orbit, or apogee, from sea level on Earth, of 2,339 kilometers, which is actually quite a bit further. It's quite a bit into the mid-Earth orbit range, but this is just for a temporary transfer orbit. You can think of it as kind of a taxi between getting off of Earth and getting to its final orbit. And if we do the orbital math for period again, we get 6,782 seconds, which again is going to be larger than the 5,555 seconds of the final orbit. Now, the third question is, how much delta V does each satellite need? So with the transfer orbit, if you just let the satellite go at perigee, it would follow the same orbit that it was originally intending on, which is the transfer orbit. We don't want it to do that. We want it to, in theory, slow down from the transfer orbit into its final orbit. So we can simply use a modified version of the Vis-Viva equation here, which is negative mu over 2a equals negative mu over r plus v squared over 2. And solving for velocity, that gives us a v equals square root of negative mu over a plus 2 mu over r. Now, plugging in for 3.99 times 10 to the 5 for mu, we get a velocity final. So this is going to be the final velocity of the final orbit of 7.672 kilometers per second, which is really fast. Now, all we have to do is solve that same equation for the transfer orbit, getting a velocity of that orbit for 8.3136 kilometers per second. Subtract the two to get the change in velocity between the transfer orbit and the final orbit, hence the delta, and we get a delta V of 464 meters per second. So each satellite has to change its velocity by 464 meters per second to get from the transfer orbit to the final orbit. So from there, it was a simple thing of listing out all of these orbital characteristics and then working from the satellite's point of view. So we actually have 3 more questions to answer for these satellites themselves. So the first question that I wanted to know was, because these satellites aren't going to be just communicating with the ground, but with each other, what is the distance that the communications would have to travel from satellite to satellite? Now, my primary goal with this was to try and figure out what kind of lasers or antennas or whatever communication means I'd be using, what they would have to be rated for. So for this, I needed, again, the number of satellites, the radius of the Earth, the semi-major axis of the orbit, and I was solving for the distance between satellites. Now this one was actually incredibly simple because I had an inscribed circle, or an inscribed polygon, that was also circumscribed. So it was a simple matter of 2 times the semi-major axis of the orbit times sine of pi over 9, which gave me a communications distance of 4,637 kilometers. So whatever communications mean, like if I'm using a laser, it has to be rated for probably comfortably around 5,000 kilometers, since none of these numbers are perfect. The next question that I had to answer was, what is going to be what I'm calling the swath length of each satellite? So each satellite is going to have a certain viewing portion of the Earth that it can provide communication services to. Now, this is primarily going to depend on the antenna that I equip it with. But I decided to go with a 30-degree arc from each antenna, because that's a pretty standardized antenna. And for the math was even more simple here, where I get tangent of 15 degrees. That is half the 30 degrees because I'm working off of a right triangle. Tangent of 15 degrees equals the swath length over the 409 kilometers orbit altitude that I had calculated for. And based off of that, I got a swath length of 350 kilometers. So the surface area of this theoretical constellation would be the circumference of the Earth by 350, would be the circumference of the Earth long and 350 kilometers wide. So then the last question I had to answer was the eccentricity of the transfer orbit. So no, I'm not talking about what is the personality of the transfer orbit, but rather, how circular is it? So this is the math right here. Let me quickly get into frame. And so eccentricity is measured in orbital dynamics as a number between 0 and 1. So to give you perspective, a very low eccentricity is going to be a very elliptical orbit, whereas a very high eccentricity is going to be a very circular orbit. So for the transfer orbit, I measured an eccentricity of, and bear with me here because it had to be very precise, 0.1246126,033. Now, the reason behind it being that precise was that I was going to base a lot of other calculations off of this. So now I have the numbers that I would need to simulate this. I have the orbital period for the final orbit. I have the semi-major axis of the final orbit. I have the orbital altitude for the final orbit. And I have the perigee and apogee of the final orbit. For the transfer orbit, I again have the orbital period, semi-major axis, perigee, apogee, and also the eccentricity. And for the spacecraft, I have the delta V required per satellite, I have the distance between satellites, and I have the swath length. The next step for this is going to be to simulate it.
Okay, so here we are in Kerbal Space Program, or KSP. Now, Kerbal Space Program is usually viewed as a game, although there is a certain mod set called Realism Overhaul that makes it into a pretty decent space simulator. So here we have a basic communications satellite that I've put together, and this is what I'm going to use for the satellite constellation that I'm going to put around low Earth orbit, or the theoretical constellation that I'm going to put around low Earth orbit. So it's your pretty standard communication satellite built around a probe core with 2 omnidirectional antennas for satellite communication, 1 relay antenna for ground communication, and 2 solar panels for electricity. I'll just fold those back up there. But the main thing that I want to look at here is the solid rocket booster. Now this is going to be what gets this satellite from the transfer orbit down to the final orbit. From the perspective of the Earth, the satellite will be slowing down into its final orbit, although it'll actually be speeding up because of orbital mechanics. So that's what the delta V that we calculated was the change in velocity. So this solid rocket booster is what's going to be providing all of that delta V, and it will have a burn time of 1 second and a delta V of 465 meters per second, because that is the closest I could get to the 464 meters per second that we need. A good way to think of delta V is in terms of car commercials. Whenever they say this car can go from 0 to 60 miles an hour in so and such time, well, this satellite can go from 0 to 465 meters per second in 1 second. And so you might see some other stats here. We have our thrust to weight ratio, TWR. We're not going to worry about that since we're not on Earth when launching this, but what that means is if the weight of this rocket were 1 kilogram, this booster provides 42.8 kilograms of thrust. The actual thrust of this booster is 181.8 kilonewtons. So Newton and kilonewton is a term of force, and the ISP is the specific impulse. So that can be the efficiency of the rocket motor, where if you're thinking of your car in terms of miles per gallon, for rockets that is specific impulse in seconds. The mass of the satellite is going to be 432 kilograms, and that's really all the important stuff out of the way. Now, how I got to this delta V, that was through the mathematics that I calculated out, but I then had to make a custom solid rocket motor for this satellite to achieve that. And so what I did was I just played around with the diameter, length, and solid fuel level until I got it close enough, which was the 465 meters per second. So now we can try launching this, after saving, of course. Okay, so we're not actually going to be launching this satellite into orbit because this is just a test to make sure that this satellite can get from its transfer orbit to its final orbit. So the first thing that we're going to do is we're going to activate at least one of these antennae. I like to activate two of them simply for redundancy. Then we're going to go to Orbit Editor and we're going to go to Complex. We're going to set our inclination to be 0, so from the perspective of Earth again, this satellite will be in an equatorial orbit. Now, here's why those numbers were so valuable from what we calculated. Now we can simply input the eccentricity. We calculated out to be 0.1246126.033. The semi-major axis we calculated out to be 7,744 kilometers, but since this is measured in meters, we have to add 3 zeros onto the end. And we can set the epoch to now. And congratulations, we are now in orbit. So now we can turn on the Smart SAS, which will let us kind of steer the satellite. Now, in actual satellites, they have things like magnetorquers and reaction wheels to do this. And we can point retrograde relative to the orbit. So now, we can go to the map view. So this is kind of the view of the orbit satellite. And we can see, among other things, 2 previous test satellites, but also the Earth. And we have a periapsis of 408 kilometers, just like we calculated, and an apoapsis of 2,338 kilometers, just as we calculated. So now, if we speed up time until we're right before our periapsis, or perigee, rather, and we go back to retrograde, speed up time again, right click on here, and now we're going to be looking at the top. This number is our current altitude, and the dial to the left is our altitude changing. So as soon as that hits 0, we're going to activate that engine, and that was pretty chaotic, but in that second we changed our apoapsis to be where our periapsis was, and now if we look at it, our periapsis is 3,399 kilometers, and our apoapsis is 408 kilometers. So that is pretty close, only a few kilometers off, which is an acceptable margin from what our ComSat should be. So that was just testing the delta V of that motor. The next step for this would be to test this with a satellite bus carrying 9 satellites, release 1 at the perigee and every orbit, and do that same maneuver where we fired off the solid rocket motor. But that will be for another video. For now, this has been Christopher Texler, and see you next video.